proper way to bond separate cabinets is to the equipment grounding conductor of the circuit breaker cabinet. According to National Electrical Code Section 250.30. A2. The equipment grounding conductor shall be connected to the system grounded conductor of the service, at each separately derived system, and at each transformer secondary over 150 volts to ground. In this case, the 600 kV amps delta Y transformer is considered a separately derived system, and the Y neutral is the system grounded conductor. Therefore, the equipment grounding conductor for the circuit breaker cabinet should be connected to the Y neutral at the transformer. Once the equipment grounding conductor is connected to the Y neutral at the transformer, it can then be used to bond the separate cabinets. The equipment bonding jumper for each cabinet should be connected to the equipment grounding conductor in the cabinet. This will ensure that all of the cabinets are bonded to the transformer's equipment grounding conductor and to the building grounding electrode. Connecting the equipment bonding jumpers to the building grounding electrode is not explicitly required by National Electrical Code Section 250.30. 8.2, but it is often done as an added measure of safety. However, connecting the equipment bonding jumpers to the circuit breaker cabinet equipment grounding conductor is the most direct and effective way to ensure that all of the cabinets are properly bonded. Let's delve a bit deeper into the concepts and code requirements discussed, breaking them down for clarity. Firstly, let's define a separately derived system. A separately derived system, as it pertains to electrical installations, is a premises wiring system whose power is derived from a source other than a service. This source could be a generator, a transformer, or even a battery inverter. The key characteristic is that it has no direct electrical connection to the service conductors of the building. In the context of the 600 kV amps delta Y transformer mentioned, the secondary side of the transformer, which provides the 480 volts power, constitutes a separately derived system. Secondly, consider the equipment grounding conductor. The equipment grounding conductor, or EGC, is a critical component of the electrical safety system. Its primary purpose is to provide a low impedance path for fault current to flow back to the source, thereby facilitating the operation of overcurrent protective devices like circuit breakers or fuses. This low impedance path helps to quickly clear ground faults, minimizing the risk of electric shock and equipment damage. The equipment grounding conductor can be a wire, a metal raceway, or even the metal enclosure of electrical equipment, provided it meets specific requirements for conductivity and mechanical integrity. Thirdly, regarding bonding versus grounding. Bonding refers to the intentional connection of metallic parts to create an electrically conductive path that ensures electrical continuity and the capacity to safely conduct any fault current likely to be imposed on it. Grounding, on the other hand, refers to connecting the electrical system to the earth, which provides a reference point and helps to stabilize voltage during transient events. Bonding and grounding work together to provide a comprehensive electrical safety system. Now let's elaborate on National Electrical Code Section 250.30. A2. This section of the National Electrical Code specifically addresses the grounding and bonding requirements for separately derived systems. It mandates that the equipment grounding conductor must be connected to the system grounded conductor. In the case of a Y-connected system, the system grounded conductor is the neutral point of the Y. This connection is crucial because it establishes the necessary path for fault current to flow back to the source, enabling the overcurrent protection devices to operate effectively. The code also specifies that this connection must be made at the source of the separately derived system, which in this scenario is the 600 kV amps delta Y transformer. There are several reasons why connecting the equipment grounding conductor to the Y neutral at the transformer is the preferred method. One reason is that it provides the most direct and effective path for fault current to flow back to the source. By connecting the equipment grounding conductor directly to the neutral at the transformer, any fault current will have a low impedance path to return to the source, which will facilitate the rapid clearing of the fault. Another reason is that it helps to minimize voltage differences between the various metallic parts of the electrical system. When all of the metallic parts are bonded together and connected to the same grounding point, it helps to equalize the voltage potential between them, which reduces the risk of electric shock. Now let's discuss the implications of connecting the equipment bonding jumpers to the built-in grounding electrode. While connecting the equipment bonding jumpers to the built-in grounding electrode is not explicitly required by National Electrical Code Section 250.30 A2, it is often done as an added measure of safety. This practice provides an additional path for fault current to flow back to the source, which can further enhance the safety of the electrical system. However, it is important to note that connecting the equipment bonding jumpers to the built-in grounding electrode should not be considered a substitute for connecting the equipment grounding conductor to the Y neutral at the transformer. The primary path for fault current should always be through the equipment grounding conductor, with the connection to the built-in grounding electrode serving as a supplementary measure. Finally, let's examine the importance of bonding the separate cabinets together. Bonding the separate cabinets together ensures that all of the metallic parts of the electrical system are at the same voltage potential. This is important because it reduces the risk of electric shock and helps to prevent the buildup of static electricity. The equipment bonding jumper for each cabinet should be connected to the equipment grounding conductor in the cabinet, which in turn is connected to the Y neutral at the transformer. This arrangement provides a low impedance path for fault current to flow back to the source, ensuring that all of the cabinets are properly bonded. Now, let's address the potential concerns raised by field personnel regarding improper connections. It's not uncommon to encounter varying opinions on grounding and bonding practices, even among experienced electricians. This is often due to a lack of understanding of the underlying principles and code requirements. One of the most frequent points of confusion is the difference between grounding and bonding and the specific requirements for separately derived systems. To address these concerns, it's important to provide clear and concise explanations of the code requirements and the reasons behind them. Emphasize the importance of following the National Electrical Code guidelines and the potential hazards of improper grounding and bonding. Offer training and educational resources to help field personnel better understand these concepts. Document the grounding and bonding procedures in a clear and easy-to-understand format. This will help to ensure that everyone is on the same page and that the correct procedures are followed consistently. Now let's examine some potential scenarios and address common misconceptions. A common misconception is that connecting the equipment grounding conductor to the built-in grounding electrode is sufficient for bonding the separate cabinets. While this may provide some level of grounding, it does not provide the low impedance path required for effective fault current clearing. The equipment grounding conductor must be connected to the Y neutral at the transformer to provide the necessary path for fault current to flow back to the source. Another misconception is that using metal conduit or raceway is sufficient for equipment grounding. While metal conduit and raceway can serve as an equipment grounding conductor, they must meet specific requirements for conductivity and mechanical integrity. It's important to ensure that the conduit and raceway are properly installed and maintained to provide a reliable grounding path. Furthermore, consider the impact of using shielded wiring within the cabinets. Shielded wiring is often used to protect sensitive electronic equipment from electromagnetic interference. The shield of the wiring must be properly grounded to prevent the build-up of noise and to provide a path for fault current to flow back to the source. Typically, the shield is connected to the ground bar within the cabinet, which in turn is connected to the equipment grounding conductor. It's essential to ensure that the shield is properly terminated and that the connection to the ground bar is secure and reliable. Let's also address the situation where cabinets are not connected together using metal conduit or raceway. In such cases, it's even more critical to ensure that a dedicated equipment grounding conductor is run between the cabinets. This equipment grounding conductor provides the necessary path for fault current to flow back to the source and ensures that all of the cabinets are properly bonded. The size of the equipment grounding conductor should be determined based on the size of the circuit conductors, as specified in the National Electrical Code. In conclusion, properly bonding separate cabinets in a 480 volts power system is essential for electrical safety. The equipment grounding conductor must be connected to the Y neutral at the transformer, and the equipment bonding jumper for each cabinet should be connected to the equipment grounding conductor in the cabinet. While connecting the equipment bonding jumpers to the built-in grounding electrode is not explicitly required, it can be done as an added measure of safety. By following these guidelines, you can ensure that all of the cabinets are properly bonded and that the electrical system is safe and reliable. Also, let's discuss the importance of periodic inspections and maintenance. Electrical systems are not static, and over time, connections can loosen, components can degrade, and insulation can break down. Regular inspections and maintenance are essential to identify and correct any potential problems before they lead to safety hazards or equipment failures. During inspections, pay close attention to the grounding and bonding connections. Ensure that all connections are tight and free from corrosion. Check the integrity of the equipment grounding conductors and bonding jumpers. Look for any signs of damage or degradation. Test the grounding impedance to verify that it is within acceptable limits. If any problems are found, take immediate steps to correct them. This may involve tightening connections, replacing damaged components, or rerouting equipment grounding conductors. It's also important to keep accurate records of all inspections and maintenance activities. This documentation will help to track the performance of the electrical system and to identify any trends that may indicate potential problems. Consider implementing a formal preventative maintenance program. A well-designed preventative maintenance program can help to extend the life of electrical equipment, reduce the risk of failures, and improve overall safety. The program should include regular inspections, testing, and maintenance activities. The frequency of these activities should be based on the type of equipment, the operating environment, and the manufacturer's recommendations. Provide training to maintenance personnel on proper grounding and bonding techniques. This will help to ensure that they are able to properly inspect, maintain, and repair the electrical system. In addition to inspections and maintenance, it's also important to consider the impact of any changes or modifications to the electrical system. Anytime changes are made, such as adding new equipment or rerouting circuits, the grounding and bonding system must be reevaluated to ensure that it is still adequate. It's important to consult with a qualified electrical engineer or electrician to ensure that all changes are made in accordance with the National Electrical Code and that the electrical system remains safe and reliable. Finally, remember that electrical safety is everyone's responsibility. Encourage all employees to be aware of the potential hazards of electricity and to report any unsafe conditions to management. By working together, we can create a safe and reliable electrical environment. Let's also expand on the different types of grounding systems. There are several different types of grounding systems that can be used in electrical installations, each with its own advantages and disadvantages. The most common types of grounding systems are solidly grounded systems, impedance grounded systems, and ungrounded system. In a solidly grounded system, the neutral point of the transformer or generator is directly connected to the earth. This type of system provides a low impedance path for fault current to flow back to the source, which facilitates the rapid clearing of faults. However, it also results in high fault currents, which can cause significant damage to equipment. In an impedance-grounded system, a resistor or reactor is inserted between the neutral point of the transformer or generator and the earth. This impedance limits the fault current, which reduces the risk of equipment damage. However, it also slows down the clearing of faults, which can increase the risk of electric shock. In an ungrounded system, there is no intentional connection between the neutral point of the transformer or generator and the earth. This type of system offers the highest level of service continuity, as a single ground fault will not cause the system to trip. However, it also makes it difficult to detect ground faults, which can increase the risk of multiple faults and equipment damage. In the context of the 600 kV amps delta Y transformer, the secondary side is typically a solidly grounded system. This is because it provides the best balance between fault current limitation and fault clearing speed. However, in some cases, an impedance-grounded system may be used to reduce the risk of equipment damage. When selecting a grounding system, it's important to consider the specific requirements of the application. Factors to consider include the size of the electrical system, the type of equipment being used, and the level of service continuity required. It's also important to consult with a qualified electrical engineer or electrician to ensure that the grounding system is properly designed and installed. Now, let's delve into the specific requirements for sizing the equipment grounding conductor. The National Electrical Code provides detailed guidelines for sizing the equipment grounding conductor based on the size of the circuit conductors. The size of the equipment grounding conductor must be sufficient to safely carry the fault current back to the source. The specific requirements are outlined in National Electrical Code Section 250.122. In general, the equipment grounding conductor must be sized no smaller than the size of the circuit conductors. However, in some cases, a larger equipment grounding conductor may be required. For example, if the circuit conductors are installed in parallel, the equipment grounding conductor must be sized based on the total ampacity of the parallel conductors. It's important to carefully review the National Electrical Code requirements and to consult with a qualified electrical engineer or electrician to ensure that the equipment grounding conductor is properly sized. Let's also address the use of ground fault circuit interrupters or GFCIs. Ground fault circuit interrupters are devices that are designed to protect people from electric shock. They work by monitoring the current flowing through a circuit and tripping the circuit if they detect a ground fault. Ground fault circuit interrupters are required in certain locations, such as bathrooms, kitchens, and outdoor areas. However, they can also be used in other locations to provide additional protection. Ground fault circuit interrupters are not a substitute for proper grounding and bonding. They are a supplementary safety device that provide additional protection in the event of a ground fault. It's important to ensure that all ground fault circuit interrupters are properly installed and tested to verify that they are functioning correctly. Also, let's discuss the importance of surge protection. Surge protection devices are designed to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power outages, and other events. Surge protection devices work by diverting the surge current to ground, thereby protecting the equipment from damage. Surge protection devices are available in a variety of types and sizes. They can be installed at the service entrance, at the panel board, or at individual pieces of equipment. It's important to select surge protection devices that are appropriate for the application and to ensure that they are properly installed. While surge protection devices can help to protect equipment from voltage surges, they are not a substitute for proper grounding and bonding. They are a supplementary safety device that provides additional protection in the event of a voltage surge. Finally, let's reiterate the importance of following the National Electrical Code. The National Electrical Code is a comprehensive set of standards for electrical installations. It is designed to protect people and property from electrical hazards. It's important to follow the National Electrical Code guidelines when designing, installing, and maintaining electrical systems. The National Electrical Code is updated every 3 years, so it's important to stay up to date on the latest requirements. Copies of the National Electrical Code can be obtained from the National Fire Protection Association or from other sources. It's also important to consult with a qualified electrical engineer or electrician to ensure that the electrical system is in compliance with the National Electrical Code.